So I've kind of alluded to the fact that the next model we are going to look at is a straight line. But before we take that for granted, let's take a look at why using a straight line to model anything might be a good idea. So let's consider the problem setting. Suppose we now want to predict the value of y for any given value of x. So for example here, let's say x is the average of a child's parents' height. So it's the average height of the child's mom and dad. And the y we're looking at is the child's height. So I want to predict a child's height given the average height of the child's parents. One reasonable thing we could try is to predict the average y value for each x value. So for example, suppose we want to predict what a child's height will be if their parents' heights average to 70 inches. Well, what we could do is look at all of the observations that we already had whose parents' average height was 70. So all of these y values here, and predict the average of all of these y values. Why would we do this? Well, we spent an entire lecture talking about why the mean or average of a set of values minimizes average squared loss when it comes to predicting a summary statistic for those values. So it makes sense to use the mean or average here. Now, just averaging the y values when x was equal to 70 won't give us perfect results, because while it looks like all of these points here are clustered around x is equal to 70, some of them might be like 70.1 or 69.9. And so what we instead want to do is look at a small range of values around x is equal to 70, which is kind of what we've done here. These two red lines define a small window centered around x is equal to 68. And so this yellow dot that we have right here is the average y value of all of the dots that fall into this window of width 1 centered at x is equal to 68. If we apply this average of a bin technique to positions along the x-axis, the result looks like this set of yellow points that we have here. Now, these yellow points roughly correspond to the average value of y for every x. And we can see that this plot looks roughly like a straight line. And so that is why we are choosing to use a straight line to model this relationship. It's because this graph of averages looks like a straight line. Now, the simple linear regression line, again, is not new. We actually saw it in Data 8. The simple linear regression model is of the form theta naught plus theta 1 times x. So here we have two parameters, theta naught and theta 1. And the way we make our prediction y is we take some constant, theta naught, which we call the intercept term, and add it to theta 1 times x, where x is our input variable, which we didn't have for the constant model, and theta 1 is what we call the slope. Now, for simplicity's sake, instead of calling it theta naught plus theta 1 times x, we will temporarily call it a plus bx. There's no real reason for this other than that it's more familiar, perhaps, from Data 8. More generally, we will use something that involves thetas. So this is the simple linear regression model. And as we did for the constant model, to find the optimal model parameters, so a hat and b hat, or theta naught hat and theta 1 hat, what we need to do is choose a loss function and then minimize average loss across our entire data set. So as I mentioned at the end of the last lecture, squared loss is the loss that is most typically used. And so if we choose squared loss here, meaning that our average loss is a mean squared error, the optimal model parameters are given right here. The optimal value of b hat, is equal to r, the correlation coefficient, times the standard deviation of y divided by the standard deviation of x. The optimal value of a hat, or the intercept term, is the average of our y's minus the optimal slope, b hat, times the average of our x's. Now, in the next video, we are going to derive by hand where these optimal model parameters come from. We are going to do the same thing we did in the last lecture, which is take a derivative, set it equal to 0, and solve for the optimal parameters. But for now, let's take a look at a demo where we implement these optimal model parameters by hand and see what we get. Okay, so let's take a look at what we have here. And as always, this notebook will be posted on the website, so you can play around with it on your own if you want to. So our first step is implementing the correlation coefficient R by hand. Momentarily, we are going to look at how to compute the correlation coefficient using built-in NumPy and pandas methods, but I think it's a good exercise for us to do this now. We know that the definition of the correlation coefficient involves a set of values in standard units, so I've also defined a standard units function that takes in a list of values and returns that same list of values, with each of them converted to standard units. So it's value minus mean of value divided by standard deviation of values. Cool. And the correlation function takes in two lists of values, or arrays I should really say, and returns the mean of their product in standard units as the formula we looked at described. So let's load in our data, and it's the same data where we have the average, parent's height, and child's height. Now, one issue with the data that I have here is that the parent and child's heights occur at spaced out fixed positions on the x and y axes. So for example, you can see here, the child height 61.7 appears, many times, and the, parent height 69.5 appears many times. These are likely, slightly rounded versions of the original data. And so what I've done is I've added a little bit of random noise or jittering to both the x and y axes just so that we can see the spread of the data a little better. We will have some severe overplotting if we don't do this. And so let's take a look at a scatter plot of our data. And to create this scatter plot, I've used the plotting library called Plotly, which allows us to create interactive plots like this one. Like you can see, I can hover over a point and it will tell me the exact x and y coordinate. Anyways, here on my x-axis, I have the average height of a parent, and on the y-axis, I have the child's height. It's the same data that we just looked at in the slides, and you can see that the simple linear regression line, or line of best fit, should roughly look something like this. It should pass through the middle of this point cloud. Now, let's call our hand-built correlation function and see what it tells us. So the correlation is 0.44, which tells us that there's a mild positive linear association between x and y. Just to make sure that we've done everything correctly, we can use the built-in NumPy correlation function, which takes in a set of arrays, or a matrix more generally, and it gives you the pairwise correlation coefficients between all of the columns in the matrix or all of the arrays that you've passed in. And so what we're interested in here are the elements on the diagonals, which exactly match up with what we have here. So it looks like we've done everything correctly. The reason we have ones on the diagonals is because this top left one is the correlation coefficient of parent height with itself, and of course a value is perfectly positively associated with itself. We can also use the inbuilt .core method of pandas on data frames, and it sort of gives us the same result as np.correlation coefficient, but the result is a data frame. Anyways, that was besides the point. What we will now do is apply this sort of graph of averages technique to our values. And so don't worry too much about how this code is operating. It's really just implementing the procedure that I outlined here. And again, you could play around with it if you wanted to. But if we look at the result, you can see that these yellow dots correspond to our graph of averages. And these are our, average value of y for every given value of x on the x-axis. Now, what we will now do is use the definitions of A and B that we just looked at in lecture to create our simple linear regression line and see how well that matches this yellow sort of graph of averages, right? Because the whole point is to use a line to model this graph of averages. So here I've used my correlation function to define my function that will give me the slope, or B, which is the correlation times the standard deviation of y divided by the standard deviation of x. And I wrote an intercept function, which will give me the value of a, which is the mean of my y's minus the slope we just computed up there times the mean of my x's. So if I run this, I have these defined. And now if I run this code, it will compute what the intercept and slope should be. And I've written a nice little print method, which will tell me the exact equation that we are using to predict child height from parent's height. So maybe this should say parent average parent's height here. Cool. And so what this is telling me is that the intercept or value of A is 26.51 and the slope or value of B is 0.61. What this is saying is that the best simple linear regression model is the one where you predict child's height by taking 26.51 and adding that to 0.61 times the average of the parent's height. Let's take a look at what this looks like on our scatter plot. And you can see that this red line now is the simple linear regression line that we have here. It matches very closely to this graph of averages that we have here in yellow. And so it seems like our simple linear regression line is doing a pretty good job of predicting y given any value of x. Now, you may be asking, what was the point of implementing this graph of averages here? You already actually did this in data 8. And it's because we will actually repeat this process again for when we get to logistic regression, where our goal is classification, so predicting zeros and ones instead of predicting real numbers. We will talk more about logistic regression in a few weeks, but this process of creating a graph of averages will come back, and so that's why you should be familiar with it. And again, the slide sort of summarizes the picture that we have here. Our linear model comes pretty close to the graph of averages, so it seems like a good choice of model to use.